everyone, I welcome you all in today's session. As we have discussed some of the problems in the previous session on the linear transformation, let's discuss the concept of the kernel in today's session. That's the kernel space, or we call it as a null space. So the statement is in this way that if you have given any linear transformation, let T is any linear transformation or a mapping from a vector space V to the vector space W, that it will be a linear transformation then the set of those vectors, then the set of all the elements means the vectors of the domain V, which are mapped to the zero vector of W, is called the kernel of T. Kernel of T, and we are denoting it the K of T, or kernel of T, or the null space of T. So mathematically we can say that the K of T is nothing, it is the set of all those vectors from the vector space V or F, such that T of F is equal to the zero vector in the W. So this zero of W is the zero vector of W space. That is, I will show you here that if this is my vector space V over F, and this is your vector space W as a codomain, and the function T is defined as a linear transformation from V over F to the V over W over F. So this is your domain and this is your codomain, and there is a subset here. Let this we call as R of T. It is a subset of W of F. So as you know that the vector, as V over F is a vector space, so it has its zero vector, and W over F is a vector space, it has its zero vector. We denote it by 0 W. Zero vector means the additive identity. So here the elements which are going here, there are the many elements in the V over F, and as T is a linear transformation, so it will map to the 0 will map to the 0, and there are many other vectors which are mapping to the 0 vector. These vectors which maps to the 0 is called the kernel of T, and you can see that it is a subset of your vector space, that is the domain. Okay, and you have to remember it that the kernel of T can never be empty, because 0 vector will always map to the 0 vector of W, so it always belongs to the kernel of T. Also, you have to note it that the kernel of T is always a subspace of your domain V over F. Okay, this is a subspace. So when it is a subspace, means it is a vector space in itself. So this is the kernel. Okay, as it is a subspace, as kernel of T is a subspace, so it means that it has a dimension, it has a basis. So I said here we are saying that the dimension of the set and the dimension of this set, that's kernel of T, is called the nullity of T. Nullity of T, and that is denoted by n over T, or that is the dimension of n of T. That is a nullity. Similarly, as I told you that if this is your V and this is your W, so it means that there will be a set here and there will be many other elements that would not or may not be the pre-image. So let this is the part of the image of the W, sorry, the image of V. So that means this is a part that every element has a pre-image, that every element has a pre-image. This part is called, as I told, R of T we are denoting, this is called the range of T. And you have also remembered that it is a subset of W over F, and it is, as I told, it is a subspace of W over F. So it has a dimension also, and dimension of this R of T we are calling it as a rank, and we are denoting it by rank of T. So it means that the 0 of W will be here as it is a subspace, and there is a 0 of V. So it means that this 0 of V will always map to the 0 of W, and there are many other elements from here which map to this 0 of W, isn't it? So these elements you can check, these elements which maps to here as a 0 on the 0 is called the kernel. So kernel of T is a subset of V over F. This is called the null space, and the dimension of kernel of T is called the nullity and denoted by n of T. And similarly, the range space of T, we are denoting it R of T, is the subset of W over F, even the subspace, and the dimension of R of T is called the rank of T and denoted it by the row of T. Okay, so what is, by the definition, what is the range space? So we say that let T is a function from a vector space V over F to the vector space W over F if it be a linear transformation, then the set of all elements, those elements we denoted by Y, in the W over F such that it has a pre-image. So that means Y is equal to some X, T of X, for some element in your V over F, where Y is the image of X in W. So this we call as range space or range of T, and we denote it by R of T. Okay, so mathematically what we write, R of T is the set of elements in the W of F that has the pre-image. So T of X will be equal to Y for some element in the V. Okay, okay, so it has a dimension. So as I told, dimension of R of T is called the rank of T and denoted by row of T. Okay, so as you can see, I told you that 0 of V is always going to 0 of W. So it means that a range of T can never be empty. Okay, it can never be empty. Okay, so we have one important theorem here. If T, okay, listen, if T is a function from V to W and dimension of V is equal to, let's say, M, T is a linear transformation. Linear transformation. So you have this V, this you have as a T, sorry, this you has the W, and this is a function T. So there is a subset of his that we call as a range of T. And here we have a subset that we call as a kernel of T, and you know the whole set, the image is going to the R of T. So it has a dimension that's called the rank of T. It has dimension that's called the nullity of T. So we have one theorem that is the dimension of V, that is your domain, is equal to the nullity of T plus the rank of T. So that is dimension of your domain is the dimension of the kernel of T plus the dimension of the range of T. This theorem is called the Rank-Nullity Theorem. Okay. So, for example, if you have given function, let's say you have the question in this way, that show that the transformation that's from V2 to R going to V3 over R, that's a vector space having the 2-dimension or 3-dimension, or you can take it R2 over R to the R3 over R, consider it that, such that T of A comma B is equal to A plus B, A minus B comma B. So for all the elements A and B are from the R. So let this is a linear transformation. As you know, we have done this example as it is a linear transformation. Then you have to check its null space. What is its null space? That is, what is its kernel of T? Second, what is its nullity? That means what is the dimension of this kernel? Third, find its range. And fourth, find the rank of T. Okay, so we discuss this problem in the next session. You try this once, so let's explain it in the next session. Thank you very much. Please subscribe and share the channel.